This is Module 16, Lecture Notes 31. Today, the module is about something called redox reactions. And redox is a word that's short for reduction oxidation reactions. And these are a special type of reaction that you're going to get to explore in the lab activity. And what's cool about these is you've actually encountered them in your everyday life. When you see rust forming on a nail or on a car, that is a redox reaction happening. Batteries work as a result of redox reactions. When you see your food molding or turning colors, that is a redox reaction. And I've listed several others here. So I hope you guys have a great time in lab getting to explore some of these. But let's look at why we see these changes happen on a level of the chemistry inside the molecules. So today we're going to learn how to assign oxidation numbers to different compounds, okay? And an oxidation number is just the charge that an atom in a molecule would have if the most electronegative atom took the electrons from the less electronegative atom, okay? Going back to the first part of chemistry, remember that something that's electronegative has a really strong desire to attract electrons. Okay, remember it really, really wants just a few more electrons in order to be like the nearest noble gas. Okay, you probably will want to pull your old periodic table back out as we're going through these today. So let's look at an example together. We are going to assign oxidation numbers to the molecule HCl. Okay, remember that when hydrogen and chlorine are bonded to each other, hydrogen brings 1 valence electron and chlorine brings 7. Okay, is it kind of coming back to you now? And they're going to share these 2 electrons in a covalent bond. Okay, so remember that when they are sharing them, it's not really an equal tug of war. Chlorine has much more desire to fill its octet, and so it's really going to have a tight hold on this bond. And when it has that extra electron, remember when you gain negative friends in your life, you become more negative. And that would make hydrogen more positive. Okay, so in this example, hydrogen would have an oxidation number of +1 and chlorine would have an oxidation number of -1. Okay, overall, the sum of your oxidation numbers must equal the charge on that molecule. Well, look, HCl is neutral. There's no charge on it when it's bonded together. So that means my +1 and my -1 should form a neutral molecule. There's no charge. Okay, so that's how we would look at this first example. Looking at these other 2 examples, I want to show you that the same element can have a different charge depending on the problem that you're given. So here, lead is neutral. It would have an oxidation number of 0. It's by itself. There's no charge on it. You will see this a lot. Now, if you're given lead with a charge, then its oxidation number is equal to the charge. Okay, so the same element can have a different charge depending on what you're working with or who it's bonding to. Okay, let's look at 2 examples before we jump into some rules down here at the bottom. Let's say that we know the oxidation number of magnesium is +2. Okay, and I'm getting that from our periodic table. Magnesium likes to lose 2 electrons. So let's put a +2 for magnesium's oxidation number. What does bromine's oxidation number have to be in order for these charges to equal 0. Okay, well, there's 2 bromines. So if each one is a -1, then we'll have a +2 from magnesium and a -1 from each bromine, and overall, this will equal 0. Okay, so we'll say that magnesium was a +2 and bromine is a -1. Let me rewrite that for you. Okay, and they must add up to 0 when you have a neutral molecule. All right, let's jump into one where we have 3 different elements to work with. Here it tells us we know hydrogen is going to be a +1. So I want you to put that right over the top. And it also tells us that oxygen is a -2, but there's 3 of them. So let's write this out down below and figure out what bromine has to be. So we have a +1 from hydrogen, and we have 3 oxygens. What does bromine have to be in order for my charges to add up to 0 for a neutral molecule? I have +1 and -6. So we need bromine to be a +5. Okay, so if we write out what we know for everything, we've said that hydrogen's a +1. In this case, bromine's going to be +5, and each oxygen is a -2. So when you're assigning oxidation numbers, you are going through and figuring out what charge that element will take within that molecule. And it's not always going to be the same. Here bromine was a -1, and here it was a +5. So you will actually have to do a little bit of work to figure out what it likes to be in each individual case. Let me go through and give you some rules that you can follow almost all of the time to know how to assign oxidation numbers for the examples that you're given. I would like you to have your periodic table handy so you can follow along with where I'm getting these numbers from. The first rule says that when you only have one type of atom that you're working with, like just fluorine gas or just a calcium ion, the oxidation number is just equal to the charge basically on that one atom. So here fluorine is neutral, there's no charge on it. This one's going to be an oxidation number of 0. You will see these single elements quite frequently in your examples. Remember that they just are a 0. Now if your element is an ion and it already has a charge, then the oxidation number is just equal to that charge, +2. Okay, so that's our first rule. Our second and third rules deal with the first 2 columns on the periodic table. Okay, remember that these metals like to give up their electrons. Okay, they like to be positive. And so it says in compounds, group 1A metals are going to have an oxidation number of +1. And group 2 metals are going to have an oxidation number of +2. These 2 rules are really nice because these guys follow the rules most of the time. Our fourth rule talks about fluorine. And remember, fluorine is our smallest atom and it also has the highest electronegativity, which means it really, really wants that last electron to be like the nearest noble gas. So it will always have an oxidation number of -1 when it's bonded to something else. Okay, rule 5 helps us with hydrogen. Remember, hydrogen is over in this column, but it's really a non-metal, so it gets kind of sticky. So here's what you should do with hydrogen. if it's bonded to one other atom that's a metal, it will have an oxidation number of -1. This is really rare. So you'll only use that in a couple special circumstances, but almost all of the time, it's going to follow the rule of its column and will have a +1. Okay, so that's what you should do for hydrogen. Oxygen, who's right next to fluorine, follows the rule of its column and it likes to gain 2 electrons, so it will have a -2. Those are the rules that apply almost all of the time, that don't change. So when we're doing examples, you're going to start with this set of rules and assign oxidation numbers to the things that we have rules for. And then you should have enough information to figure out the other oxidation numbers, like we did in the 2 examples up here. Rule 7 just says if all else fails and you need more information, just assume that the atom's oxidation number would be the same as it is in an ionic compound. And so basically you would just use the charges that we're used to. But that's only if all else fails. Okay? So we're going to flip over, and I think the best way to get really good at these is to just do some examples together. So let's do that. Okay, I'd like us to focus just on these top 3 examples. Notice that these are just single elements. They're not bonded to anybody else. So we should be using rule number 1 for these 3 examples. And our first rule just says that it's going to be equal to the charge of that atom. So if we were to assign oxidation numbers to chlorine, you should put a 0 for chlorine. It's neutral. Titanium is neutral, and then gold would have an oxidation number of +1 because the ion has a +1 charge. Okay, so these should be pretty easy. Let's jump down to assigning oxidation numbers when we have elements bonded to one another. So if we look at sodium chloride, we don't have a rule for chlorine, but we do have a rule for sodium. Atoms in column 1 like to have a +1 charge. So if we know that, then we know that chlorine must be a -1. Okay, what about magnesium sulfate? We're going to assign oxidation numbers for the things that we have rules for first. Remember, magnesium likes to be a +2. And oxygen likes to be a -2. We need to figure out what sulfur is in this compound. If it helps you to write the charges out down below, I would encourage that. So here's what we're looking at. We have +2 for magnesium, 2, 4, 6, 8, -8 for all these oxygens. And somehow we need sulfur to make this neutral. We need +6 for sulfur. Okay, I'd like you to try NaSO3. Come back and check your answer with me. So here's what I assigned for NaSO3. +1 for sodium, +5 for sulfur, and -2 for each oxygen. And here's my work below. And this is just another great example of why we can't assume what sulfur is going to be, because with redox, depending on who it's bonding to, it takes on a different oxidation number. All right, let's jump down to this last section here for some that may be a little trickier. Okay, here we have 2 carbons bonded to 4 hydrogens. Carbon is a nonmetal. So we're still looking at the rule in which hydrogen has an oxidation number of +1. So if we give hydrogen an oxidation number of +1, and there's 4 of them. We have +4. We need to figure out what each carbon should be. We know that overall we need -4, but we have 2 carbons, so each one is going to be a -2 to make this neutral overall. Jumping to this example, we have lithium, which is always going to be a +1. Hydrogen here is bonded to lots of other things, so it's going to follow the +1 rule. And we need to figure out what nitrogen should be. So here we have lots of positive charges from our lithium and our hydrogens. And that would leave nitrogen as a -3 to make a neutral molecule. And then lastly, sometimes you will see ions. This is one of your polyatomic ions, phosphate. And if you have an overall charge, instead of getting this to add up to 0 to be neutral, we need it to add up to -3. So we know oxygen is always a -2, and there's 4 of them. What does phosphorus need to be such that when we add this together, we're still left with -3? That would make phosphorus a +5, because +5 and -8 leave an overall charge of -3. You might write yourself a note there. Must add to -3 for this ion. Okay, I would like you to try these last 4 examples by yourself to see if you really have the hang of this, and then come back and we'll check the work together. Okay, let's take a look at this last section here. If you can do these with ease, then you really have a good grasp on these rules and assigning oxidation numbers. So for nitrogen trichloride, nitrogen and chlorine do not fall under any of these rules 1 through 6. So that's when we would use rule 7. If all else fails, then assume the atom's oxidation number is the same as it would be in an ionic compound. And notice I put a couple groups here that works well for. And chlorine is in group 7. And just like fluorine, it likes to gain 1 electron. So let's assume that chlorine's oxidation number is -1. And you have 3 of them. So that would mean to make a neutral molecule, your nitrogen would be a +3. Okay, jumping down to your sulfate ion, we do know that oxygen has an oxidation number of -2, and there's 4 of them. So you have a total of -8 charge on this side. Remember, when your molecule as a whole has a charge, just like we did up here, your oxidation numbers need to add up to that charge. So I'm going to assign a +6 to sulfur so that +6 and -8 leave me with a charge of -2 overall. All right, jumping down to F2CO. So let's assign oxidation numbers to oxygen and fluorine because they always follow the rules. Fluorine will be a -1, oxygen will be a -2. We can even write out our charges. We know that overall we need a neutral molecule, so I have a total of -4 with all my charges together. So in this case, carbon needs to be a +4. And then lastly, S8. Did you get this one? It is sulfur. It's by itself. It's not bonded to anyone else, and it doesn't have a charge, so it's neutral. Okay, so I think the more and more you practice, you'll get really comfortable with assigning oxidation numbers. Definitely write out the charges if that helps. And I will see you guys next week for our very last lecture.